Hey everyone, welcome to the fifth lecture in our series on imitation learning. I'm Sanjivan Chaudhary, a research scientist at Aurora and soon to be assistant professor at Cornell. Today we'll talk about the role of value in imitation learning. That is, not all imitation errors are equal in terms of value. We look at imitation learning as a game where the learner plays against the expert to improve upon its values. We'll see that this is merely the first step on a long road to self-improvement, where the learner evolves from playing against the expert to playing against itself. So let's dive right in. So we begin with the same running example that we've been using, where we wish to imitate a race car driver driving around a track. But this time we add a condition that the track is actually on top of a cliff. Now we go ahead and collect expert demonstrations and then train behavior cloning to produce a policy. As we've seen before, the policy we learned falls off the cliff because of compounding errors between train and test time. But we have an algorithm to solve this problem. That algorithm is called Dagger, that we know gives us OT errors. Dagger asks the human to label all the states that the learner visits. We would then collect these labels, retrain the policy, and eventually drive error down to OT. Notice something strange in these labels. So for the states that are on the track, the human shows corrective actions that you would expect. But for the states where the learner is falling off the cliff, notice that the arrows point in a straight direction. Presumably because this is the safest thing to do when one is falling off the cliff. Apps keep itself safe. Now we'll see that labels such as these lead to a bit of a problem. To see it clearly, let's ask ourselves, what is the best policy in the policy class that minimizes the total cumulative loss? In some sense, this is the best policy that the Dagger aspires to produce. We are now going to construct a pathologically bad policy that has low training error. So we have a policy that drives perfectly on the track, makes one mistake, goes off the track, but then drives straight thereafter. So every time you execute this policy, it always makes a mistake and goes off the track and then drives straight thereafter. We can think of this policy perfectly imitating the expert in the straight sections, right? The initial part of the curve. We can also say this policy perfectly imitates the expert when falling off the cliff, so the brown section. But this policy makes one mistake. It makes a mistake on the curves, which is a tiny fraction of the overall data set, right? So we have ourselves this interesting situation here. It would appear that the average training error is less than epsilon, right? But the policy is clearly bad. So the value of the policy, which is a cumulative cost, is clearly much, much worse than the human. But wait, don't we have an O epsilon t performance guarantee? We'll argue that this guarantee is misleading. What we actually have is a guarantee of O epsilon t times m, where this constant m can actually be quite large. And this is fundamentally because not all imitation errors are equal. To formalize our intuitions in math, we are now going to take a look at a very important lemma that's central to reinforcement learning and imitation learning. This is called the performance difference lemma. As the name suggests, it seeks to bound the performance between the learner, j pi, and the expert, j pi h. We can write this difference in terms of the value of a policy. So v pi s naught is the value of policy pi beginning at an initial state s naught. So you can think of rolling out a policy pi from a big initial state s naught and looking at the total value of this policy and rolling out the expert pi h from s naught and looking at the difference between the values of these two policies. Now, Performance difference lemma, or PDL, is a very visual lemma. So I'm going to use red and blue to track the learner and expert policies respectively. Now the key trick behind PDL is to notice that I can break up the difference in terms of two sums. We're going to add and subtract a term that looks like the value of a policy, where you roll out the learner for the first time steps to get to S1 and then roll out the expert thereafter. So we're going to keep the last term, minus v pi h, keep the first term, and then we're going to add and subtract this new term that says, that looks at the one-step cost of executing the learner and then rolling out with the expert thereafter. And since we added the term, we have to subtract it off as well. So now the difference in values is now the sum of two differences. We'll refer to these differences as the advantage. So the last two terms can be interpreted as the advantage of policy pi with respect to pi h at S0. So what do we mean by advantage? Well, advantage of policy pi with respect to pi h, you can think about it as if we flip pi h to pi for just one time step, how much does this change the values? It's quite simple. For example, let's say you're at a state st and you have a bunch of actions. Normally the expert would have chosen the action in blue, but the learner chooses a different action in red. And after that, you subsequently roll out with the expert. What is the difference in values between these two rollouts? That's essentially what advantage boils down to. All right, so let's return back to our equation. Notice that the first two terms can now be expanded and we can actually cancel out the one-step cost. And now we get difference in values at S1 instead of S0. Now hopefully you can spot a pattern, right? Initially we were looking at difference of values at S0. Now we're looking at difference of values at S1 plus the advantage. So you can keep applying the same trick of breaking up the values into smaller and smaller differences until you're only left with a sum over advantages, right? So back to our equation, we can write the difference in values as sum of t terms, where every time step t you're rolling in with the learner, right? So you're on policy. Then you measure advantage with respect to the human policy pi h, so you're rolling out with the human. So the mental image is that you're always rolling in with the learner with pi, and then you're rolling out with the human with pi h, and you're simply adding up the advantages. So PDL in a nutshell is the difference of learner value and expert value is the sum over on policy advantages. Okay, so now let's see how PDL can help us formalize our original intuition that not all imitation errors are equal. Let's look at PDL and Dagger side by side. So PDL says that the difference in values is sum over per time step advantages. So you're rolling in with the learner, but rolling out with the expert and looking at difference of values. Dagger looks at the per time step imitation loss. So you're rolling in with the learner just as before, but this time you're looking at the mismatch between the expert action and the learner action. Crucial thing is that these two terms are not the same. Let's return to the cliff example we were looking at before. Now when the race car is on the straight portion of the cliff, sure, it can take multiple actions, but for each of these actions, if you were to roll out the expert, they can recover pretty well. What does this suggest? This suggests that the advantages won't be too bad in the straight section. But on the curves, for some actions, the car can go off the track, and the advantage for those actions can be really, really high. High advantage typically means that the human cannot recover from those states. So let's take a look at what the advantage vector looks like at this state. So you have three actions. One of them is the one the expert would have chosen, that has advantage of 0. The other one is mild, has a high advantage of 10, but one of them is really bad, has a super high advantage of 1,000. Contrast this to the vector Dagger looks at, which is essentially 0-1 loss. Dagger weighs both of the incorrect actions equally. In a sense, this is Dagger treats this problem as a classification problem. On the other hand, if we were to optimize the PDL loss, we would know that some actions are far worse than others. In other words, this is an instance of cost-sensitive classification. Finally, note that we can upper bound the advantage in terms of the 0-1 loss. So the advantage vector is upper bounded by the 0-1 loss times the worst advantage of any action for that state. And we call this capital M. Notice that Dagger provides an O epsilon t guarantee for the 0-1 loss, but that in fact induces an O epsilon t M bound for the value difference. And M can indeed be quite large. So why are we optimizing the 0-1 loss? Can we not minimize the advantage directly? The answer is yes, we can, and there is a well-known algorithm to do so. It's called aggravate, and the fundamental idea is don't ask the expert for the correct action. Instead, ask them for values. To better understand this algorithm, we're going to simplify our example and instead look at a race car driving down a straight track. If you recall the Dagger algorithm, aggravate operates in a very similar manner. So the first step is to roll in the learner policy pi to get a set of states. Now, instead of asking the expert for the correct action on these states, we're going to query the expert for advantage vectors. Think of these advantage vectors as being the penalty of executing the wrong action at a state. Now, interestingly, for states that are near the edge, this advantage vector skewed heavily because it's really, really bad to go off the track. Because of this skewing, the learner knows it has to get this action correct. Okay, so back to the algorithm, we then aggregate data just like before, but this time we're aggregating state and advantage vectors. And then we train a cost-sensitive classifier to get a new policy. And this concludes the aggravate algorithm. It was published by Ross and Bagnall. Now, we have an interesting observation. For this algorithm, the learner can in fact do better than a suboptimal expert. This was not true for any of the algorithms we've seen thus far. Why? It's because when the expert tells us the advantage, they're secretly telling us something more. They're telling us something about the cost of the underlying MDP. So in some sense, if the expert does not pick the best action that has the minimum advantage, you can in fact do better than the value of the expert policy. And this will turn out to be a key step that starts to build a bridge between the domain of imitation learning and reinforcement learning. Namely, we're going to look at bootstrapping reinforcement learning via imitation. Think of this as a winding staircase where at the very bottom you have aggravate. So let's recap what aggravate is. You're solving for a policy that minimizes on-policy advantages with respect to the expert, right? With respect to policy pi h. Now keep in mind the key observation. If pi h is suboptimal, your learner will end up doing better than pi h. That suggests that at the top of the staircase is reinforcement learning, where you can think of solving for a policy that minimizes advantage with respect to itself. So we have exchanged policy pi with policy pi. So we are measuring advantage with respect to itself. And you can think of this bootstrapping process where we initially start with pi h, improve to get policy pi plus, and then improve upon that to get pi plus plus, and keep going all the way till we get the optimal policy pi star. There's been a bunch of different ways to do this bootstrapping, and we're going to talk very quickly about two. So one way is called Truncated Horizon Policy Search, or THOR, by Sun et al. And the basic idea is to simply run Bellman backups on API-H. So to imagine running a tree search on top of the advantage with respect to the expert, right? So that's one way to kind of get a better policy. Another idea is called Loki. This is by Cheng et al. And the idea is to mix the advantage with respect to the expert API-H with advantage with respect to the policy API. At this point, you can ask an even more basic question. Why do we bother with bootstrapping? Why can't we directly do reinforcement learning? Now, while this is not a lecture series on reinforcement learning, I think it's important to provide some intuition about why this might not be a great idea. Consider a toy MDP with n states, and you are at the first state. There's a pot of gold right at the end. Now, there are one action that takes you towards the pot of gold and two actions that take you back. Now, let's say you naively began by choosing actions with equal probability of a third. So this is an example of a sparse reward setting. So you have a reward of 1 at the end, at the pot of gold, and 0 elsewhere. So what would happen if we did direct reinforcement learning? So let's say we're taking policy gradients. So we roll out the current policy pi, observe the one-step rewards, sum them up, and now we are going to take a gradient of the advantage. If you evaluate this gradient, you'll see that it's pretty close to 0. Why? Well, given the MDP, the probability of seeing gold under the current policy of 1/3 is almost 0. So this is a very elegant counterexample provided by Kokade and Langford in their paper Approximately Optimal Reinforcement Learning. And they suggest a remedy called CPI, or Conservative Policy Iteration. The key idea of CPI is based on the observation that direct policy gradient gets stuck in saddle points. And this can be remedied by choosing a better exploration distribution. A distribution that sees gold with high probability. So for example, let's say we had an expert distribution that wasn't perfect, but saw gold with high enough probability. Then we could, instead of rolling in with the learner, we could roll in with this expert distribution and measure advantage on that distribution. That would be non-zero. And the second idea is that when you are updating your policy, you have to take care to make sure it's close to this exploration distribution. Maybe in the total variation distance between the two policies is small, so that you don't deviate too fast from the exploration distribution. So let's return back to the staircase. We now have a bunch of algorithms like Aggravate, Thor, Loki, CPI. We'll talk about one last algorithm, DPI, that is fairly close to the top of the staircase. DPI stands for Dual Policy Iteration, and it sort of combines the best aspects of many algorithms and ties them together with the idea of self-play. So let's imagine a game setting where we have a learner policy and we have an adversary policy. This should remind you of previous lectures. The goal of the adversarial policy is to build better advantage functions, while the goal of the learner is to improve upon advantage with respect to the adversary. Okay, so game begins by the adversary playing a policy, 8 or not, which could be the initial human policy. The learner then performs a CPI-like step where it solves for a policy, that minimizes advantage with respect to the adversary policy, eta I minus 1, while making sure the policy doesn't deviate too much from the previous policy that was played, right? So the total variation distance is less than beta. So then plays this policy pi 1. And now the goal of the adversary is to solve for a new policy that just does better on the overall value while staying very close to the learner policy pi 1, right? So it's again taking a small step with respect to the learner. And so it plays eta 1, and this step continues back and forth. And notice that both of these players are, in the end, optimizing for a singular metric, which is the advantage of one player with respect to the other, but taking very small steps when updating their policies, which is a natural thing to do when solving such games, if you wish to reach the equilibrium in a stable way. So for more details, I highly recommend checking out this paper by Sun et al. And in fact, they give concrete examples of both of these players. For example, you can think of the adversarial player being guided policy search and the learner player playing aggravate. And with that, we are at an end. So to recap, the key challenge that we discussed today is that not all imitation errors are equal. Some are much more costlier than others. So the key insight was that we should be minimizing advantage because it's proportional to the impact of an incorrect action on the value. We discussed an algorithm, aggravate, that does this. We saw that aggravate becomes a template for self-improvement where you change advantage baseline from the expert to itself. We also gave a warning that direct RL is slow and can get stuck, and one should apply the same old trick that turn RL into a game and stably reach the equilibrium. Finally, on a parting note, we are left with a question. Is this a broad principle to turn a difficult optimization problem into a game that we know how to solve? This will indeed be the topic of a future lecture, but till then, be well.